All right, so here is chapter 7. First, we want to make sure that you understand what a chemical bond is. And a chemical bond is simply defined as an attraction between two atoms. And there are two major types that we study in here. There are more types of bonds, but the two that you're responsible for are ionic and covalent. Ionic bonds are where electrons are transferred. One wants to gain electrons, the other one will lose. So then there is an attraction between the cations and the anions due to the different electrostatic charges. Covalent bonds are where we have both elements wanting to gain electrons. So electrons are shared. In order for bonds to form, electrons must interact with each other. And so in order for that to happen, those electron orbitals that are around the nucleus have to be close enough to overlap. In a covalent bond, all of the electron cloud density will then surround both nuclei. In an ionic bond, we have an electron or more that's being transferred, and then there is an electrostatic attraction between your positively charged ion and your negatively charged ion. In order to predict bond type, we had already learned that ionic bonds form when one wants to lose and one wants to gain. So metals want to lose electrons and non-metals want to gain electrons, and that results in that transfer of electrons. Covalent bonds happen when both elements want to gain electrons. And so because it's nonmetals that would like to gain, we know that covalent bonds are formed between two nonmetals. And in that case, electrons would be shared. Now there is special cases looking specifically at covalent bonds where we can call the bonds polar, okay? Polar or nonpolar. In a nonpolar bond, that means there are no poles of charge. So both atoms have the same attraction to those electrons, and thus they have the same electronegativity values. Electrons will be shared equally in nonpolar bonds. However, in polar bonds, each atom will have a different electronegativity value, which means the electrons will be more attracted to one element than the other. For example, fluorine is the most electronegative element. If you have a bond between hydrogen and fluorine, those electrons are going to shift closer to the fluorine because it's more attractive. So electrons in polar bonds are shared unequally due to those different electronegativity values. An example of a nonpolar bond would be if you have two elements that have the same or very close to the same electronegativity values. For example, here we have chlorine, a Cl2 atom. Each Cl atom has Cl2 molecule, each Cl atom has an electronegativity value that's equal to the other one. So the electrons are not going to be more attracted to one than the other. They're going to be shared equally. However, in a polar bond, here we see carbon and oxygen. Oxygen has a higher electronegativity value, and so the electrons are more closely attracted to the oxygen, and that means that they will slightly shift. Now, this is not the same as an ion transfer or an electron transfer. Okay, there is no full charge that's moving. It's just a shift in where the electrons would like to be, which makes the oxygen side just slightly negative, and the carbon side in this carbon-oxygen bond just slightly positive. It's not a full charge. Ionic bonds are where you have a full transfer of electrons. So now you have an actual charge on the atom that is different. And it's these alternating charges in the ions that cause ionic compounds to form these crystal structures, where everything is very perfectly aligned and the different types of ions are alternating. And here's an example of a sodium chloride crystal. And you can see it alternates between cations and anions. And that's to make sure that the repelling charges are as far away from each other as possible while still being part of this crystal structure. So if differences in electronegativity determine the polarity of a bond, they also help us determine bond type. If there is a very high difference in electronegativity values, we'll have an ionic bond. Metals versus nonmetals have a very different electronegativity value, resulting in that ionic bond. If there is a mid difference and you have two nonmetals, and there's a slight difference in electronegativity values, then we will have a polar covalent bond. And then finally, if there is little or no difference between electronegativity values, our bond will be nonpolar. So we consider anything that is in the difference range of 0.5 down to 0 a nonpolar covalent bond. Polar covalent is in that midsection, and anytime we get to a difference that is greater than 2.1, or an easier way to tell is, do you have a metal bonded with a nonmetal, then it's definitely going to be an ionic bond. We can calculate the difference in electronegativity, which we can look up what the electronegativity values are for each atom. That's never something you're expected to memorize or know. You are supposed to know the trends on the periodic table, and comparing based on their position, you would need to be able to tell which one is more electronegative than the other. But the actual values of electronegativity is something that you'd be expected to look up, not something to memorize. We can see if we have a nonpolar bond, iodine, I2. Each iodine has the same electronegativity value, resulting in a 0 difference. But carbon and oxygen have an electronegativity difference of 0.89. That results in a polar covalent bond. Going back to valence electrons, something that we've been looking at a lot lately, electrons all will pair up. Okay, they exist in pairs. Remember, spin up, spin down. Electrons are much happier when they are paired up. We can have lone pairs of electrons and bonded pairs of electrons. Lone pairs get their name because they stay alone. They do not bond. Single electrons in any Lewis-Dot structure would like to become bonded pairs. Okay, and so that helps us predict the charges. And you were doing that in lab yesterday or the day before. One of those during your labs for chapter 7. You were looking at how many bonds do each of these types of elements want to make. So those unpaired electrons would like to form bonds. If you have a pair of electrons in your Lewis-Dot structure, they're not going to bond. They're going to stay by themselves, and they're happy already. They don't have to be involved in the bonding unless it's necessary to complete the octet or 8 valence shell of something else. Okay, so looking at what the octet rule is. All elements want to have the same electron structure as a noble gas, which means that most elements want 8 valence electrons, except for if we're comparing to the helium atom, which has 2, so hydrogen would like 2. So 8 valence electrons are stable. And if we look at the example of water, we see oxygen wants to have 8 electrons, right? And so it's able to get the 2 hydrogens to share their electron with it, so that then it has 8 surrounding its nucleus, which means, let me go back, sorry, whoops. Okay, the reason why water is bent is the oxygen has these 2 lone pairs of electrons. And they're actually going to repel these bonded pairs to cause them to end up in this bent shape. Okay, linear molecules very often have no lone pairs of electrons, cause that bent shape. An isomer is a molecule that has the same molecular formula but different structures. So for example, here you were being asked to build C2H6O in one of your chapter 7 labs, and you were to come up with different ways to connect those atoms to make C2H6O. Ethanol is one way and dimethyl ether is another one, and we can see that even though they're made with the same atoms, they are very different in structure. And that's an isomer. That is what the word isomer means. Iso meaning the same. Mer just means part. If you think of the word mermaid, part woman. Isomer, same parts. Okay. You've also had experience building molecules that have double and even perhaps triple bonds. So each bond represents 2 electrons that are being shared. Single bonds, are 2 electrons, double bonds are 4, and triple bonds are 6. There can be no quadruple bonds, okay? It's either single, double, or triple. And here we can see examples of the Lewis-Dot structures when we're looking at how are bonds going to form and what exactly causes double or triple bonds. And it has to do with making sure to fill that octet. Okay, that refers again to the 8 electrons that we want around the nucleus of each atom, with the exception of hydrogen that only wants 2. Going back to this idea of lone pairs of electrons causing changes in molecular geometries, we have a theory called valence shell electron pair repulsion theory, which looks like VSEPR but is often referred to as VSEPR theory. And that theory tells us, since electrons like to pair up, and since electron pairs are negatively charged and repel other electron pairs, because like charges repel, molecules will be shaped so that the electron pairs are as far apart from each other as possible. Okay? So, if we look at carbon dioxide, there are no lone pairs of electrons on the carbon. There are just these 2 double bonds. Those 2 double bonds will try to be as far away as possible from each other, causing a flat line. Okay? 180-degree difference. That's as far away as we can get those electrons from each other. If we look at formaldehyde, that was another one I had built when we were talking about lab 7B. It has a double bond, a single bond, and another single bond. So you have 3 areas of electrons that want to repel each other. So it causes this triangular shape with a 120-degree difference between each of those bonds. And then finally we have 4 bonds. This is methane, and you'll notice that each bond is as far away from each other as possible, and that's what causes that tetrahedral shape. Notice it's not a square, because a square would be flat in one plane. Here we can actually get those electrons farther away from each other if it turns into a 3D shape. Okay, this just explains a little more why 180 degrees is as far as we can get those bonds from each other. When we have 3 areas, again, a triangle is the farthest we can get those all from each other. And finally, the tetrahedral shape is so that we can get those away from each other. This also helps explain why ammonia, NH3, pops up into this triangular pyramid shape as opposed to being a flat triangular planar shape. And it's because nitrogen has a lone pair of electrons. So this actually takes on a shape just as if it had 4 areas of electron density, but it's not tetrahedral because it's not bonded to a top atom. So depending on our numbers of lone pairs of electrons, we can have different molecular shapes even though we have 4 areas of electron density. The tetrahedral shape has 4 bonded pairs. The trigonal pyramidal shape has 3 bonded pairs and 1 lone pair. And the bent shape has 2 bonded pairs and 2 lone pairs of electrons. All right, so here is the homework assignment. It's been on the board, and if you have questions, feel free to post them on the board.